Well, hello again for some of you. Okay, so I'm talking in this section on MOOC-based hybrid pedagogies, and I have a confession to make. Although my group and I have run 5 MOOCs, we didn't start with the MOOC. We started with the on-campus pedagogy for which we needed preparation for the students, and that turned into the MOOC. So from here on, if I say MOOC, that's what I mean. Okay. Now, and these are the people who helped develop a lot of the pedagogy here. So when you take this title, kind of, generally, whoops, excuse me, I want to get my stopwatch here so that I know when to stop. I also have a starting watch to know when to start. So what online stuff are you going to blend with what on-land stuff? I mean, you've got 2 sides of the equation now. And I'm going to just start off with using eText usage as a measure of student engagement. And I'm going to show you this picture here of the average number of pages viewed in the eText by the student per day throughout the course of the fall semester from September to December. Okay, you see that curve? I'm going to ask you a question. How many examinations do you think there were in this course? Okay. Very good. Now, you'll notice that the instructor intended the students to use this every week to do their homework, right? But you can see right there what happened. The students tried it, and as soon as they went to the first exam, they realized that was pointless. So they don't use it the way we think. Okay, now I'm going to show you this traditional online. Okay, so this is what happens when you have a traditional course, say, and you have an online eText. The students have a lecture, and then they have the eText. You get curves like this green one also when you have a MOOC that has videos and it has the eText. Okay. It turns out then the students don't use the eText at all, except they use it much, much more to review for the test. They use the text, not the videos. Okay, and this is, it should be our on-campus course, but it's actually our online course, but it's similar to our on-campus course, except it falls off a little more. Okay, so there's, again, you see these exams here in traditional. When you have exams, you see it. When you have a continuous distribution of quizzes every week, then you see a much more uniform use of the textbook. In fact, if you alternate the quizzes every week, the textbook use spikes up in between. I don't know why, but that's what we've observed. Okay. Now, there's another way of looking at this, and that is, look, I don't care when the kids read the textbook. I just want them to read every page that I wrote in my textbook, okay? So this is a graph of what percentage of the students have read over what percentage of the eText pages. So these are when you have a lecture or you have a print textbook and you also have an online textbook. And these courses I often call 17-17 courses. Okay, that is to say 17% of the students have read more than 17% of the text. So you can estimate, you square that number, and you can figure out what fraction of the pages were actually read by, it's pretty small. Then when you have traditional tests, but this is the only textbook, then you get up to this green area. And now when you have weekly tests, or generally what we might call reformed, or you might call flipped, then you get up into this region where in the course of the semester, 70% of the students have accessed more than 70% of the pages in the eText. Okay, so I would say from this that the conclusion is you should not just take the online stuff and duplicate the traditional way of teaching, or you're going to get very low engagement. Okay, so now, probably that's speaking to the choir, as we say. So we have this hybrid pedagogy, and we're going to use a flipped classroom. And the idea of the flipped classroom is that the students are going to learn foundational things and hopefully be brought up to an even foundational level before class. Okay, that's great. And then class is going to become more interactive. I mean, Carlos said that the great future of MOOCs is in blending them. The great present of them, I think, right now is they raise the following question, especially for private universities in the United States. What are students paying $40,000 a year for that they can get for free on the internet? Because the lectures on the internet are as good as or better than I can give in the class. Okay. So we have to deal with those questions. And what it really comes down to is, what should we be teaching students in college? And so I want to give a couple of different perspectives on that, because I really think we all have to think about that more carefully than we have been. So, of course, in the United States, we have a big political fight now about a National Academy-based Common Core standards for states. There's an organization, P21, Partnership for the 21st Century Learning, and they say it very well. In this, they've added to the 3 R's. Maybe you don't speak colloquial English, but the 3 R's are reading, writing, and arithmetic, which is pretty bad spelling. And then the 4 C's, which is better spelling: creativity and innovation, critical thinking, communication, and collaboration. So there's a broad consensus that these are the kinds of things that we should be teaching students. Okay, there's another community that goes about this. Oh, yes. And then I have to say, all this reform talk is just talk until you have some way to assess it. And this is a real problem, because it's much easier to determine whether someone can do arithmetic than whether someone is a creative thinker. Okay. Now, I want to ask a question here. DBER. How many people know what those initials stand for? Okay, that's typical. Well, 1 or 2, yeah, maybe it's a small audience. It stands for Discipline-Based Education Research. In fact, I'll come out of the closet, as we say, and say, I am a discipline-based education researcher. I am fundamentally a physics teacher, and I've been active in creating technology and pedagogy to teach physics better. And I've learned a lot in the process. Another approach, this is very valuable reading, and it emphasizes the value of reform. Okay, so we, in my group, which is Relate is the name of the group, we thought we'd explore what instructors think you should teach. And here's the result. We broke up what you should teach into the course content, the philosophy, problem solving, and relation to the outside world. And what we found was that, number one, teachers wanted to teach fewer topics. They felt they weren't teaching in depth enough. The thing that the teachers most wanted to teach was for the students not to write down these ridiculous answers. So you have 400 students, and you can put 37 students in a bus. How many buses do you need to carry the students? Answer, 9.5. Okay, that's... Think about the answer. Does it make sense? And then notice, we don't want to teach the relation of the stuff that's the physics to the world. the physics is abstract and it's beautiful and it's canonized by Newton, and that should make it fascinating to you. It turns out that's a problem, but I won't get into that problem. Okay, now let me look at this from a different point of view. Let me look at it from sort of a cognitive perspective. At the bottom of the hierarchy, there's facts, like F equals ma if we're teaching mechanics. There are procedures. You draw the body with the forces on it, and you write down the equations. There's the strategic knowledge, where you look at a problem and you say, oh, darn, because of the way the friction is, energy isn't conserved. I'm going to have to use F equals ma to solve this problem. And then there's the adaptive expertise, which is where you can create new things and new ideas with this, okay? Now, on top, let's put something underneath these. Here we go. Textbooks, lectures, peer instruction, all about facts and concepts, right? Homework problems, usually problem sets in most examinations are about procedures and operations. Maybe if you have some really tough problems, you have the challenge problem on the homework. That gets to a little bit of strategic thinking. So most high-stakes tests are over here. That's how everyone gets into MIT, is being able to do those things. And most publishers make products there. But now let me look at things a different way in pedagogy. Let's just say that there's cases where the teacher gives a problem, has a known answer, and the teacher knows how the students are supposed to solve it. That's black. Next is, there's a known answer, but there are several ways to solve the problem. And then in blue, and then in red, there's unknown answer, and you need a novel solution. Okay, now let's see, all the black is over there on the left. Now let's put in some blue. If you have a challenging exam, it's strategic. If you have to figure out a good way of checking your answer, you don't know how to do that. There's lots of ways to check the answer. See if it makes sense. If you have to estimate, you know, the standard problem is how many piano tuners are there in Chicago? That's a Fermi problem. Or what's the total revenue from all of the satellites that circle the Earth right now? I mean, those are estimation problems. No clear way you have to go about solving that. Basic research, designing things, good PhD theses. And then in here, I'm going to talk about MAPS, and it stands for Modeling Approach to Problem Solving. And it is a pedagogy we have developed that has some success at teaching students strategic thinking. Okay. So I've already talked about these three things, that the idea is we're going to try to make strategic experts. And so I'm going to talk about MAPS in the remaining time that I have, and some evidence that it actually works. This is the assessment question. Okay, so it turns out there is a wonderful test called the class, it's a survey, and it's built on some earlier work by some of the great people in physics education research, in particular David Hestenes, who also invented the force concept inventory, if you've ever heard of that. But that's the mother of all concept tests. And this asks students whether they agree with questions like this. And this is a very, very common complaint of students. I read the book, I think I understand it, but I don't know how to start the problems. And that's because the book doesn't teach strategic knowledge. So our goals are that students solve problems in a host of ways, better by getting their answer right, starting with a conceptual approach, because their knowledge is better, with better attitudes on this Colorado learning thing, and with some success at transferring what they learn in problem-solving mechanics over to the next course in physics, which is electricity and magnetism, which was invented a couple centuries later and is quite different. Okay. So the idea is to solve problems like experts. And there's a lot, this is really referring back a lot to the expert novice literature, of which not the first, but the really big impactful paper is Mickey Chi's paper on how students and experts go about solving simple physics problems. And the big difference, the big thing that sets the experts apart from the novices is the novices are in there trying to get the answer, and all their mental energy is devoted to getting the answer. And the experts see the solution as a process of solving the problem, to start systematically and plan how you're going to do it, and then figure out, is the answer sensible, are things sensible the way they're going along. Those habits of mind, many of them are transferable. Okay, and secondly, there's the organization of knowledge and how it's all interconnected, because you have to be able to interconnect and understand the differences and similarities of energy and momentum and force and angular momentum before you can have the strategic knowledge to look at a problem and figure out which of those categories it belongs in. Okay. So the way that we chose to do this, and I have to give in that first picture, the guy on the right, Andy Paul and I had so many discussions, I would say politely, about how to do this. It took us a long time, and then we would present it and people would give us feedback and we'd try it out. Okay. So we came to, and a lot of this is based on David Hestedy's papers, which are pretty indecipherable. That's one of the arguments we used to have about David's papers. David was a philosopher as an undergraduate, and he doesn't always write down to the level of me. But he made the distinction between models and modeling. And you represent your knowledge as models, and then you do the modeling to make it, to solve the problem. So you differentiate between the models, which represent core principles, and the solving process. And so basically it's like the models are the theory, they're hierarchies, it's all existing knowledge, and on the right there, the modeling process is student constructed knowledge, and it applies this organization to figure out the problem. And the connection is down here at the bottom. So what's a model? See, here's the trouble. How many people here know F equals ma? Well, you've heard that, right? Probably second most famous formula in the world. But what you don't appreciate is F equals ma is not like 3 equals 2 plus 1, which we all agree is true. F equals ma, the force is the net vector force of all the rest of the world on this point particle. It only works for point particles, only works for a single point particle. If you want to consider collisions of particles or systems of particles, you have to use momentum. And then you only consider the external forces. You don't consider the forces between the particles. The momentum model is different from the F equals ma model. And yet I remember in freshman physics debating with the class for about 20 minutes, and the instructor couldn't help. What was the real difference? Because you have to understand that these are not formulas, these are models. Okay. So this is daunting for the students in physics, and I'm sure you guys are all taking notes just as fast as you can, and you realize that it's important to remember this for the rest of your life. No. Okay. The idea is very simple, and I will quickly go over it. Mechanics is about how force changes motion. Okay. Now, we can represent the motion in terms of velocity or momentum or mechanical energy or angular velocity or angular momentum. You've probably heard of all those things, but those are the key core models. Now, when you have a model, you have to say, what is my system? And I'm going to throw everything else in the world out of the system, and maybe I'll allow some forces to come through. But this is what you do whenever you make, I think it's why Western science overtook, and Europe overtook Chinese, but I won't get into that. I'll discuss that later. But the Chinese believe in the one. Everything is indivisible. And the idea of Western reductionism is to reduce it. And so you have to say in your model, what's your system? And now the system, as I said, for this is F equals ma down here, is single particle, multi-particle here. Here you could have an extended, a rigid body like this. Or you go over here, you could have a system of rigid bodies. But all these models apply to different systems, and they apply with different interactions. And then, yes, then you can get down to these, what actually the force, what particular aspect of the force does the change. Well, I don't expect you to memorize it all, but this is the idea. Across the top, there are different core models, and down the sides there are the components of those models, the systems, the interactions, the forces, the model, the equations, okay, and so on. So I just took a while to figure that out. Okay. Now, given this is what we want to teach the students, we have to, the students need better pep relations, so that's why we made this online stuff. And in addition to that, we have to coach the students. So the class is 80% of the students working problems in groups. 10% is introduction to what's really important. You know, I mean, not a lecture, but just highlight what you're supposed to have learned. And then there's some, we'll watch the students do the problems. All the students are doing problems on the board. And you'll sort of, oh, geez, like four of my 10 groups have just this problem. So, hey, wait a minute, guys. Okay, that sort of thing. Okay. And so a teacher and a TA can handle about 10 groups. So it's rather. So I want to give you a perspective on what we've done here. So we've taken the lecture, and probably you know here, especially in Europe, which is where the lecture really started as far as I can see. And this is a typical picture of a 14th century lecture. And those are notebooks, not books, because this is before Gutenberg. And then you have homework after that. And now the modern flipped classroom looks like this. It's one professor and a small group of students. And in fact, it's not new either. Yes?
Are you suggesting that the flipped classroom is not possible with large classes?
That what?
I mean, your pictures show it. In the lecture, you have many students. And in the flipped classroom with Socrates, you have just 2 students. Are you suggesting that...
You don't, okay, so the difference is you don't have only 3 students. You have 3 students here, 3 students there, 3 students there, there are 3 students there. And they're doing work together, and you walk around and you watch, you can see the work on the board. You can see where they are, and you walk around and talk to them very briefly. You ask them Socratic questions, but you don't listen to the answer. They have to figure it out. They hate you for this, but it works. Okay, so here's a couple students doing this thing. Okay, so now what are the successes of this thing? We started it off in a 3-week course in our January for students who had gotten a D, the grade of a D, not an F, but not good enough to go on in freshman physics. And so then we didn't need a lot of the online stuff. So we started developing the teaching method and then moved it to the spring with the online stuff. But okay, so those are the students we got. That's how they did on the MIT final exam, down a little more than minus 1.3 standard deviations. And at the end of 3 weeks, they were up at 0. They were up at class average. So that's pretty good. Second thing is the class. So I'll tell you a little bit more about the class. It's a series of questions, and if you disagree with the ones in red, you're an expert. And if you agree with the ones in black, you're an expert. Okay, so all these questions, is a Likert test. You either agree or you disagree. So if you say, after I study the book, I can't do the problems, then you're not an expert. Okay? Or if you say, I have to memorize many, many formulas to do physics problems, experts don't have to memorize them all because they're all interrelated. Or if you say you enjoy physics problems, or physics, I understand that physics comes from a few principles. Those are expert views. And so this is called the Colorado Learning Attitudes Towards Science Survey. And one of the very interesting things about this is that the research shows that practically all introductory physics courses in the United States lower the expertise of students towards learning science. In fact, this gray curve is the national average, or the average of the 10 places they tested it out. And this is MIT. See, we're doing better than that, but we're still negative. The students take this great course, and we put a tremendous amount of energy into it, and they come out less expert in their attitudes towards science. And in our course, after 3 weeks, we've undone the damage that was done in the previous 3 months, and a little more. Okay. So that's very encouraging, because there are only a couple courses, and most of them that I know about are based on modeling that actually improve students' attitudes. And then, finally, there's this wonderful correlation between students' grades in mechanics and their grades in E&M, 801 and 802, the spring the fall and the spring. And so we took these kids for 3 weeks and we put them back in their course with their cohorts. And, well, I can blow up that low end of the curve. So these are the kids who had gotten in this region here and who had taken our course. And the previous year our course wasn't available. And so a lot of these students were given a passing grade of C, even though they didn't deserve it. And this is how they did when they went into E&M. Now, this is what we're trying to fix now. These are less well-prepared students. Really, these students should get an F. And we're not making a big dent on them in the 3 weeks. I think we are in our extension to the semester, but I don't have the data here. This is an interesting point, because this shows the students who had received an F, a failing grade, and therefore they had to take another 3 months of introductory physics. But after they took that, of course, they had to get a grade of C. So they had to be up here someplace in their skill. But still, you predict their E&M grade, their next grade, from the first time they took physics. So the second time they took the traditional course, they didn't learn any transferable problem-solving skills. They just learned how to do the problems on the physics exam. Okay, so, and then this persists throughout the semester and all the exams in 802, but I won't get into that. So let me just summarize what I've said here. First of all, MOOCs and online things should blend with reformed teaching. Secondly, we should be moving the students past facts and procedures. I mean, the students in our class, they have to do some communication. They have to do some collaboration. And we have to help. We actually do some work to make the groups work better. Sometimes we switch the groups around or whatever. The general goal, I think, of what we're trying to teach is expertise. And I gave you an example of a particular one. But the thing that I like about it is that we have objective measures that show that it's at least some steps in the right direction. So that's what, I hope that online education can bring to on-land education. Thank you very much.
There's some time for questions.
Yes.
One of the major problems that colleagues and myself, and it seems across the fields, are facing in Germany and Austria is absenteeism of students. Do you have that? Or
Is what of the student?
Students
Oh.
not coming to classes.
Well, yeah.
Third of the students are not coming to classes.
Okay, fine.
Across universities and fields.
Okay.
And do you have problems of this kind?
Okay, I'll make a statement. Okay. In our lecture courses, it used to be that at the beginning of the semester, the attendance was around, well, not the first day, everybody comes the first couple days to find it, but after like the first 2 weeks, the attendance would be 60, 70%. And then many cases towards the end, it would be less than 50%. Okay, for attendance at lectures. I never complained about that because I didn't think the lectures taught them anything, approximately. Okay, so now when we switched to this pedagogy and we correlated all the activities that we had of the students, you know, their homework, their class performance and so on, we found the number one thing that correlated with the final exam was how much they came to class. At which point I said, okay, now I feel it's okay, coming to class and performing in the class is worth 20% and another 5% for our judgment of how well you're doing. So that solved the attendance problem pretty much, except near the end of the term for the kids who've done really well on the